In this video, we're going to talk about another type of partial differential equation, and that is the wave equation. Here's the title. So, let me just go ahead and write down the general form of the wave equation, and that is y t equals to a squared y x x. So, the y means, in similar to the heat equation, the y in the wave equation, instead of meaning the temperature, it means the displacement of the string. So for a string, so this is the neutral, sort of a neutral position, that if you have bouncing back and forth, and so the bouncing back and forth right here, so the displacement right here, this is going to be your y, and then this is going to be your x, and then also you know what time is, right? So that is t. So before you do anything, you should also be able to identify the value of a. So the question will give you the value of a2, and also you should be able to easily figure out what the value of L is. So let's separate the variables. So instead of in the heat equation, t is the first derivative. The wave equation will have t to the t of the second derivative. So x t equals to a squared x double prime of t. Okay, just side note. Do you know what? Think about this ytt for a second. What is the y means displacement, and what is displacement? The second derivative of displacement, and that's right. If you learn physics, you'll be thinking about acceleration, and you'll be exactly right. So this is the acceleration term. Oh, sorry. Okay, and then rearrange. So let's get back on track. Rearrange this equation that we'll have x double prime of x equals to t double prime of a squared t equals to negative lambda. So again, I'm just telling you the trick here. Always set that equal to negative lambda where lambda is greater than 0. And then again, whatever the constant always follows the t, not the x. So let's set up the differential equation. So x double prime of x equals to x double prime of x equals to negative lambda, and that will give us x double prime plus lambda x equals to 0. And this is the exact same thing that you saw when you're doing the heat equation. And so let's just skip that really quick, and let's just go through that really quickly. So characteristic equation, r squared plus lambda equals to 0, r equals to positive or negative square root of lambda of I. So our x is the same as before. X equals to c1 cosine square root of lambda x plus c2 sine of square root of lambda x. So, and then just differentiate it just for fun. Square root of negative square root of lambda c1 sine square root of lambda x plus c2 square root of lambda c2 cosine square root of lambda x. And then we'll do the same thing. We apply our boundary condition and then find the value of lambda and xn, or x, if you will. So we have finished up finish what we need to do for now in order to solve for x. So now let's turn our attention to solving the t. So T is here a little bit different compared to the heat equation. So let's go through this step by step. So T double prime of T over T equals to negative lambda. Oh, sorry, I forgot an a square term over here. So that will give us T double prime plus a square of lambda T equals to 0. So characteristic equation, r square plus a square lambda equals to 0, and that will give us r equals to positive or negative square. Actually, let's write our a term first. A squared of lambda I. So our time equation will become t equals to c3 cosine a lambda square root of lambda t plus c4 sine a square root of lambda t. There you go. So let's just differentiate that for fun. T prime equals to negative a squared of lambda c3 sine a square root of lambda t plus a square root of lambda c4 cosine a square root of lambda t. It's just calculus, right? It's just, it's not, I always tell myself, it's not really hard, it's just writing. Okay, enough of jokes. Let's formulate. Oopsies, my bad. Let's formulate y of x t equals to infinite series. Okay, so here's the interesting part. A n or b n or both x n t n. So I'll explain that what the a n and b n means really quickly. So again, we can solve this differential equation in two ways. One, use the remaining boundary condition to find an or bn or both, as well as n. If possible. Or I'll use the second, or the other way to solve this is that, let me just write down the general solution for this wave equation. Y of x t equals to infinite series of n equals to 1 a n sine of m pi over l x, and then times cosine m pi and over l a t, and then plus another infinite series bn cosine m pi over l x, and then another cosine m pi over l a t. So an important observation we must make is that this infinite series contains the solutions for initial initial displacement only. Displacement of fx only. And then this, the second term of the infinite series, contains the solution of initial velocity gx only. Okay, where an equals to 2 over L integral from 0 to L fx sine m pi over L x dx, and the Bn equals to 2 over, instead of L, it is m pi a 0 to L gx sine m pi over L x dx. My recommendation is always use this method first. If you can't solve it, then use this equation, because you really don't want to memorize these equations. They are terribly long, and it is just not it is just not a right approach to learn and then solve differential equations like this. So let me move down a little bit just for better visual clarity. Okay, and then once we understand all of these, let's go ahead and look at two different special cases for wave equation. So the first one is wave equation with initial displacement only. So and again, you based on the question that you're given, you should be able to figure out the value of A and L pretty easily. Okay. So the boundary condition for the wave equation with initial displacement only is that y and of 0 and then t equals to 0, and then y of L and t equals to 0, and then so this is the key part, that y x 0 equals to fx, and then y t of x and then 0 equals to 0. So what this boundary condition means is that again, so similar to the heat equation with 0 temperature end, is that on the end of the strings, that the displacements will be always 0 regardless of your how the time evolves, in how the time changes. So that is also applied to the y of Lt equals to 0. So that just means that string is fixed on both ends. And then this important boundary condition is that it tells you that at the time of 0, it gives you the initial displacement of your string, of your string wave, if you want to say that. And then again, for this y of t, what is y of t? What is the first derivative of displacement? And that is your velocity. So at the t equals to 0, there is no velocity. Once you understand that, we can go ahead and solve our differential equation. So the first condition is that x 0 equals to 0, similar to what we did in our heat equation. So this gives us C1 equals to 0. Again, if you look at our x expression, and in order at x equals to 0, in order to let this entire expression equals to 0, c cosine becomes 1, c1 then has to equals to 0. So that will leave us our x term equals to c2 sine square root of lambda x. So, and then let's use our second boundary condition, and that is xl equals to 0. And that will leave us sine of square root of lambda l equals to 0. Again, we cannot c2 equals to 0 since c1 is already 0, otherwise the solution is trivial. So what this tells us is that square root of lambda l equals to m pi, right? Because again, if you look at the coordinates, that for sine equals to 0, the value inside sine has to equal m pi. So square root of lambda becomes m pi over L. This is important, so let's make that pink. And then lambda equals to n square pi square over L square. Let's move this coordinate a little bit further. All right, we're done with x, so let's turn our attention to t. So our t differential equation is t double prime plus a square lambda t equals to 0, and that leaves us to r equals to positive or negative a square root of lambda I, and then t equals to c3 cosine m pi over L a t plus c4 sine m pi over L a t, because we already know what the value of lambda is. So I'm just plugging that in. You know what? Let's just leave it there. Let's just switch back to lambda. Okay, so this is our t expression, but we're not done yet because we have this boundary condition that we haven't used. Actually, not this boundary condition. Instead of this boundary condition. So if we differentiate this t, what you get is cosine becomes sine, sine becomes cosine, because yt at x and 0 equals to 0. You see that we differentiated right here, that if we plug in 0 right here, that this whole term cancels, becomes 0, because sine of 0 equals to 0. Our cosine of 0 becomes 1. In order for this whole term to be 0, c4 has to be 0. So now we have come to the conclusion that c4 equals to 0. So this is going to be, so now we arrive to our final expression for t, and that is t equals to c3 cosine c3 equals to cosine square root of lambda at. All right, now let's formulate our solutions for our differential equation. Therefore, y of x t equals to infinite series of n equals to 1. So an, because again we only have the initial displacement, so we only have initial displacement, so we only have a term. And then it is xn and the tn, and this equals to infinite series of n equals to 1 an. So x equals to sine, we plug in our value of lambda, and that is m pi over l x. We do the same thing for t, and that becomes cosine m pi over l times at. So, and then we still have one more equation that we left. One more boundary condition that we left at the end that we have not used. So let's use that right now. Last boundary condition. So let's let our y and then x equals to x and then t equals to 0. So this will give us that our solution that we formulated here will become infinite series of n equals to 1 and an sine m pi over l x, and again cosine of 0 is 1, so this blue term of the t term will become 1, and that equals to our fx. And then we're just gonna solve for an and the n, and then plug them into our expression that we derived right here. And this is how you solve the wave equation with initial displacement only. All right. Before we move on to our next special case, I want to talk about something that is called the Allenberg solution. So the Allenberg solution so let fx be an odd function with period of 2L. So period, I'm just writing p equals to 2L. And contains initial displacement only. Then so if you want to find the displacement at a certain x and a certain t, so y of x and t equals to so any x and any t, as long as valid values will equal to 1 over 2 f x. Sorry, I'm trying to write the f better here. F plus x plus at plus f x minus at, and then where f x, well, f of x, this x is the value of the whole thing of x plus at or x minus at, and that equals to infinite series of n equals to 1 an sine m pi l x. So I just said a bunch of things that you might not completely understood yet, but let me explain. Remember that so as you might have noticed that the Edinburgh solutions quite resembles to our boundary condition that we just had, right here, that we had in our initial displacement only case. So if you if you know the pattern, if you know the pattern of initial displacement for the function that you're trying to solve, you can just plug, you can just find the value of x plus at and x minus at, and a is the same a as you are you know how to solve them right here. So let's just do an example. For a periodic function, for an odd function, like this. So let's just do this is 2 and this is 1, and then if I want to find and this is fx, and then let's do an extension right here that so if I want to find the value of the displacement at y of 2 and 1, so maybe 2 centimeter and 1 second. So I'm gonna find the x plus at and then x minus at. So just be careful about the odd function, the Fourier series value at x equals to 2, because the value of fx at 2, it is not here nor here. Instead, it is the average between the discontinuities. So x plus at will give me 1 because x is 0. Sorry, not here. So x plus at. By the way, let's assume that the a value equals to 1. So then my f of x plus at will become 0, or not actually 0. Sorry, my bad. X plus at, so that is f of, what is it? 2 plus 1, and then this is f of 2 minus 1. So you're just going to find the corresponding value on the fx. So let's say f2 plus 1, so that is 3 and 1 right here. So your value of this at 3 will be right here, and then 1 will be right here, and this corresponds to 0.5, and this corresponds to negative 0.5. So our solution for y of 2, 1 equals to 1/2 of 0.5 plus negative 0.5, and that equals to 0. So this is just a quick example of how to use the Edinburgh solutions to simplify our problem solving process and land our solutions more quickly. So I'm going to erase this right here because it's not very tidy. So all right, enough of this side topic. Let's move on to our second case, and that is wave equation with initial velocity only. So I'm just gonna copy and paste our title, since it's basically the same. Okay, and then wave equation with initial velocity only. All right. So again, you should be able to figure out how to find the value of A and L pretty easily in your problem description. So let's write down our boundary conditions then. So y of 0 t equals 0, y L and t equals 0, y x 0 equals to 0, and y t x 0 equals to gx. So now our strings are still fixed on both ends, but we don't have any initial displacement, and we only have initial velocity, because the first derivative of displacement is your velocity. Okay, let's focus on the x again. So x 0 equals to 0. That will give us c1 equals to 0, because again, this is the same thing as you would get in our initial displacement only. But let me just show you that if you plug in x 0 equals to 0, this cannot be 0, so c1 has to be 0, where c2 is just gone, becomes 0. Eliminated. X then will become c2 sine square root of lambda x, and xl equals to 0. So that gives us sine square root of lambda x equals to 0, because we cannot let c2 0 again. So square root of lambda times L equals to m pi, and that gives us square root of lambda equals to m pi over L, and lambda equals to n square pi square over L squared. All right, let's focus our attention to t double prime plus a square lambda t equals to 0. So this is the same thing that we tried to solve right here. So it's the same thing that we discussed right here. So I'm just going to copy and paste that down really quickly. Actually, let me just go ahead and write that really quickly instead. So characteristic, so our root of this differential equation is r equals to positive or negative a square root of lambda I. So our t equals to c3 cosine pi over L A T. Actually, just lambda. Let's not just plug in lambda A T plus c4 sine square root of lambda A T. Okay. Okay, let's use the boundary condition, because since we have no initial displacement, so because of that, this will tell us that c3 equals to 0, because again, when we plug in t equals to 0, this term gets eliminated, and then cosine of 0 is 1, and then so t of 0 equals to c3 equals to 0. So this leaves us to our final expression for t, and t equals to c4 sine square root of lambda a t. All right, and then the final and let's formulate our expression for displacement. So y of xt equals to square root of infinite series of bn again, so in this case we only have initial velocity, so no an but bn, xn times tn equals to infinite series of n equals to 1, bn sine square root of, not square root, let's plug in our value of square root of lambda, that is m pi over lx, and then sine m pi over l at. So this is our solution for the initial velocity only term. And then again, we still have one more boundary condition that we have not used. So let's do that. Last BC. So we need to differentiate our solutions that we generated right here. So let's do that quickly. Ut x0 equals to infinite series of n equals to 1, because we are differentiated with respect to t. According to the chain rule, all of these constants have to come out. So that gives us m pi a over l times bn. Sine term does not, so x term does not change, so it's still again sine m pi over l x. And again, if you differentiate this sine, you get cosine, and cosine of 0 equals to 1. So again, times 1 equals to gx. And that is your initial velocity profile. And finally, solve for bn and n. And then plug them back into your solution that you just expressed above. And this is how to solve a wave equation with initial velocity only. All right, we cover a lot in this video. So about how to solve wave equation, and then talk about two special cases, with initial displacement only and then initial velocity only. And then between that, we talk a little bit about the Allenberg solutions, which is a little shortcut to solve initial displacement only equation if you want to know the displacement at a specific time and location. So there you have it. I'll see you in the next video, where I will talk about the topic of semi-infinite domain. All right, see you in the next video.